when we set this alpha, the amplitude of the alpha less than 1, and by rating this cosine phi, we are telling ourselves that this A and D divided by 2, this result from matrix elements is equivalent to this the sufficient condition for stability. Okay, and this is more like a formula, but this is the more like a comparison between the cavity length with respect to the radial curvature of the length. Okay, so if you want to have more physical intuition, then you look into this expression. And when you do calculation, for example, in MATLAB, you use this formula. Okay, and important thing is that when we talk about stability, it's all about the comparison of the cavity length versus the radial curvature of the mirror. Okay, and later we're going to see some graphic illustrations that will help you to grasp the concept. Now, this continue to simplify the system. Let's assume that you have a system that is a symmetric cavity, like this. Okay, right here. Let's assume it's a symmetric cavity like this. Okay. Now you have a symmetric cavity consisting of 2 identical mirrors with a radial curvature of R, and then you construct the length array. You're going to see that you don't need to have 2 lenses in the system in the unit cell anymore. You just include 1 length that is sufficient. Okay, because unit cell by definition is a cell repeating itself in the length array. Okay. Now, if you just adopt this length and also this free space propagation as the ray matrix for this unit cell, then the unit cell is much simplified. The unit cell matrix is much simplified like this. Okay. But you have to bear in mind, now when we talk about n plus 1, n plus 2, n plus 3, every increment in n means a one-way, a single trip propagation in the cavity. It's not a round trip propagation anymore, because one unit cell just defined as the ray propagation from this mirror to the boundary of the second mirror. So it's every unit cell represents, and also will tell you the a single trip propagation, not a round trip propagation. Okay, but still you can extract the stability condition from the calculation. So now it's much simplified, and then you write down the stability criterion. Previously I told you that you can write down this if you know the ABCD matrix, or you can just use the laser G parameters. Okay. Now you don't have G1, G2, because G1 and G2 are the same. Because F1 is equal to F2. You only have laser G parameter. There's no G1 and G2 anymore. Okay. And so if you write down the stability criterion, you end up having this condition. And here it's quite obvious that if you want to set this condition to satisfy magnitude that's the 1, then it's a comparison of L to 2 times the focal length, or L comparison of L to the radial curvature of this mirror. Okay. For example, if you have the length, this length, equal to the radial curvature, this means that the center of this is going to match to this point. The center of this is going to match to this point. Then you will be on the border of the stability. Okay. If the L is equal to 2f, if L equal to 2f, then you have 1 minus 1 equal to 0. 0 is less than 1, so it satisfies the stability criteria. Okay. So this is how you design your cavity. But then let's try to understand how the position or angle of the ray will evolve subject to some injection condition. And that, in fact, is some sort of experiment you can do. We did this experiment quite some time ago, and the results satisfied the theory rigorously. So that was quite amazing that through this calculation, you can predict precisely the rate position and also the angle instant on those mirrors. Okay. So previously we have this, and I asked you to solve for S0 by yourself, subject to the ABCD matches, and immediately we have this result from this calculation, right? So if you have this expression and also ABCD matches, you can get this results. And this is not a difficult one. You should just calculate it by yourself. And you see that this is X, IN, the input beam position, just like what we have on the last page right here. And for this one, you end up having the S0 to be a function of the radial curvature and also the input conditions. Okay, so this is the results. And then you have a stability criterion given by this expression. Okay, and then with this expression, in fact, you can just combine these two terms, sine and cosine, into one term with some arbitrary phase in this sinusoidal function. Okay, so this is quite easy. So you just take a square of this and plus the square of this and take a square root. Then you end up having this expression with the square root. Okay, so you get the maximum amplitude for the beam positions. Does anybody have any difficulty in getting this? Quite straightforward, right? So you have something like A cosine phi plus B sine phi. You can write into square root A square plus B square sine phi plus some sort of angle. Let's call this the gamma angle. Okay, so we are doing this practice, and so you end up having some arbitrary angle here given by this expression. Okay, so basically you turn this to be sine or cosine. You turn this to be sine or cosine, and then you combine. Okay. All right. So now you realize that on the x-axis you have a maximum value and oscillating with this phi, and this phi is defined by this a plus d over 2. You can do the same thing for y, the y position of the ray, and then you also end up having some maximum amplitude, and then sine phi plus some phase that is relevant to the injection condition and also the geometry of the cavity. So in general, you have this as n that vary with the sinusoidal function, yn vary with the sinusoidal function, and don't forget this n. This n tells you that is one trip propagation inside the cavity. Could be forward trip or backward trip. Okay, when you change this n, it means that you complete one trip propagation inside the cavity. Okay, not round trip, it's a single trip. So I can sort of simplify the expression by writing this to be some sort of total phase relevant to n. And then in general, this is the ellipse on the xy plane. If you have a mirror, usually it's the circular mirror. So I put the boundary of the circular mirror here, and then subject to some input condition, all the dots formed by the laser will show you an ellipse on this mirror. It's quite beautiful, in fact, if you do the experiment. Okay, just construct a symmetric cavity, and then from one end you inject laser beam into the system, and then you're going to see this almost right away if it is stable. Is there any question? And then people tend to tend to make some special condition and make it more acceptable to for applications. If you want to generate a circle on this mirror, it's possible, right? You just need to set the angle between these two to be different by 90 degrees. So you have sine and cosine, and then you set this amplitude to be the same, then you will have circle. So two conditions. Number one, set the phase correctly, and then if this x maxima equal to y maxima, then you have a circle on the mirror. And this is the quite easy experiment you can perform if you have two cavity mirrors. All right, is there any question about this? And then if you change the, if you move the bouncing from n to n plus 1, this means that every time you change a phase equal to phi. That is the phi, in fact, is the angle. The phi is the angle on this xy plane. So when you change when you complete one more single trip, then you move the angle phi on this plane. But be careful that because whenever you change 1 in this n, it means it's a single trip. It's not a round trip. So you have to project the position from the other mirror back to the original mirror. So this is the position on the other mirror. So this is the initial position on, for example, the left mirror, and then this is the position on the right mirror. Okay, the angle between them is differed by phi. So this is how you perceive the bouncing of the light ray inside the cavity. And it's easiest that you just use a laser pointer to do the experiments. Okay, so you're going to see a lot of dots on the mirrors, a lot of dots on the mirrors. And then you can sort of adjust the cavity configuration to have an ellipse or a circle on the mirror. And this calculation is quite important for spectroscopy. Okay, usually if you want to do some absorption spectroscopy, okay, if you want to do some spectroscopy, if you just do a free space propagation, and then the power will be attenuated because of the absorption. So this is B location. But this attenuation coefficient is a function of wavelength. For example, if this is in an environment with a lot of methane, you know methane, right? It's an environmental chemical produced by biological things. You can produce a lot of methane, but if you measure the concentration of the methane or the concentration change of the methane over days, then you can construct some biological model for the environment. Okay, so this is how we do the absorption spectroscopy. Okay, and measure the using a laser to measure the absorption subject to certain wavelengths. But then the signal, the delta P is strongly proportional to the length of your measurement, because the absorption could be very weak. And what you would do is to construct a cavity like this and open a hole on it. And then you inject laser into this and bounce many, many times, and perhaps open another hole to come out to increase the length. And then you get a high contrast for the absorption. Okay, and this is the Hurra cell. Okay, there's a name associated with this, and So you need to know the trajectory of the laser beam inside this cavity so that you can make sure that the beam will exit at a certain point so that you can pick up your signal somewhere. So this is one example of using such a calculation for your application. So Li Xiaolong, you understand this, right? And I think this is quite intuitive. You need to basically understand the trajectory of the light ray based on some injection condition, and then design this cavity such that you have an exit laser for you to do these experiments. Okay. So what I'm talking about right now is not just for building a laser, but also implement some applications. All right. Is there any question? Well, it's always good to bring you back to some reality, right? Some real things, so you know that later on, if you want to do some experiments, then you know how to do it. All right, so this is sort of the trajectory of the light ray on the mirror. You can have the ellipse or circle on the mirror if you satisfy the boundary condition. Then let's look into different kinds of cavities. Well, the easiest cavity is like a parallel beam, parallel cavity, and this cavity with a radial curvature equal to infinite on the surface, and this is sort of on the edge of stability because if you just misalign a little bit, then it's going to go away. So you can see that your G1, G2. If we go back to the criterion, that is G1, G2 less than 1, larger than 0. If you set G1, G2 equal to 1, you are on the boundary of the stability. And that is why this cavity is sort of stable, but not so stable. It's right at the boundary, okay? If we just misalign this ray a little bit, then the light ray will go away. And then the second cavity, let's call it focal cavity, focal resonator. R1, R2 equal to 2L. So basically the L is equal to half of the length. The length of cavity is like this. And this is the focal length of this guy. If this is the focal length of this guy, then we call this focal resonator. And if you check this kind of focal resonator, you have G1, G2 equal to 1/2. Definitely it satisfies this condition. Okay? It satisfies this condition. And then you can calculate the periods, the phase advance, due to one wave propagation, that is 30 degrees. Okay? So if you want to complete the coming back to the same location, then you go like this: 1, 2, 3, 4, 5, 6. After the sixth round trip, you have 380 degrees. You go back to the same location. But then, if you project all those dots to this, then you just look into the location of the beam on 1 meter. Then the period is 3, just half of the period, because this is for n. When we calculate the increment of n is one way. Okay. So phi is 60 degrees, and if we go back here, if you want this beam to come back to itself, then you need to complete the 360 degrees, okay? And this will consist of the one-way propagation and so on. So if your phi is the 60 degrees, then you need to go through a single trip. 1, 2, 3, 4, 5, 6. Go back to the original location. Okay. So this how you interpret this phi. Okay. Well, we can have the third example if there's a confocal resonator. Confocal resonator is that the length of this cavity, is equal to the radial curvature of this guy. Okay. And the the center, the cavity length is equal to the radial curvature of this guy. Okay, so if you do the calculation, then you have G1, G2 equal to 0. Whoops, it's right on the stability the boundary. Now it's here. This is a planar cavity. Okay, right here is a planar cavity over here. But then this boundary is a conformal resonator right here. It's still stable. It's still stable and relatively stable than this one. And for this case, you can calculate the phi equal to 180 degrees. So this means that it has to go 1, 2, 3, 4 to come back original location. Okay, you get this phi calculation. And then you could have a concentric case. Concentric case is that you put the center of the the circle right at this location. Okay, because your L is 2R, so these two mirrors will form a circle in this case, and then you end up having this result. And then your G1, G2 is still also on the edge of stability, okay, except that you have -1 here. And then you can also calculate the rotation angle of the library. And we have more graphic illustrations, okay. So you want to design a cavity, subject to this stability criterion. And don't forget the definition of G1, G2. And there's a relationship between R and F. Okay, so this is the sort of ingredient you want to use for designing a stable cavity. And so let's illustrate that for R1, R2 larger than 0, in fact, you're going to have a cavity like this. Ooh. You don't quite confine the library with this kind of convex kind of cavity, okay? And turn out that this is unstable. This G1, G2 was larger than 1. So you are looking to somewhere here, right here, R1, R2 larger than 0. So this plot is unstable. You plot G1 and G2 on these two axes. Okay, so for this plot, you have this kind of cavity. And then, of course, after a few bounces, it's going to go away. It's unstable. Okay, you can confine the library inside. And for this one, now you the R1 less than 0, R2 less than 0. So you're changing this cavity to this cavity, this kind of cavity. And it's more promising, right? If you set the length correctly, then you can confine your library inside. And so you adjust the length of the cavity, and until it's stable, satisfying this condition, then it's in this region and in this region. Okay. The important thing I want you to do it by yourself is that the cavity length, when this total cavity length is larger than the sum of the radial curvature, then this cavity becomes unstable. And this is often asked in, say, PhD qualified exam. If you have two mirrors with the radial curvature R1, R2, then how would you determine the length between these two mirrors so that the cavity can be stable? Turn out that the R1 plus R2 has to be larger than L so that the cavity can be stable. Okay, and this is the condition that please deduce by yourself. Okay. All right. So if you satisfy, if you flip the sign, the sign to less than, then you'll be in this region and in this region. Okay, and these two regions are stable regions for the cavity. Confocal cavity, again, we have the confocal cavity on the last page. The confocal cavity is right here. The confocal cavity is right here. The radial curvature equal to the length of the cavity. For this case, you have G1, G2 equal to 0, and then it's right at this point. Okay. So the confocal cavity sort of separate these two stable regions, and I say it's sort of more stable relative to the planar cavity, because if you miscalculated the length of the cavity a little bit, it's likely that you'll be moving into this region or this region. So a confocal cavity, in fact, is a very stable cavity. If you miscalculated, if you just miscalculated the radial curvature relative to this length a little bit, you move into this or move into this. Okay, so it's quite stable cavity. Okay, but for planar cavity, if you just misalign a little bit between these two cavities, then it becomes unstable. Okay, so a lot of the laser cavities would like to adopt confocal cavity right here, and then allow some mistakes. You're going to see that you can have some tolerance if you adopt a confocal cavity, because you move into this or move into this if the R versus the L is a little bit different. Okay, and then you have the this kind of situation for what? The interesting part is this one and this one. Okay, this one and this one sometimes it's like this. You could have a cavity like this. It's convex, but then you can have a concave cavity to allow the laser to be stable inside. Okay, but if you have this kind of convex and convex mirror, then it's unstable. But if you have this kind of cavity, usually you have large laser mode size inside, and then you can extract more laser gain if you have some laser gain medium inside. Okay, and then the mode size can be larger, and then you extract more laser gain, and you can have one convex lens, a convex mirror, and then concave mirror to form a stable cavity. Okay, and this is also a sample in this region. Okay, but sometimes if you separate this too much, you fall into this region and this region. Okay, one radial curvature is larger than one means that you have a convex mirror. This is R larger than 1, but the other can be less than 0. Okay, to form this kind of cavity. Okay, so this stability diagram is very useful when you design a laser cavity. This sort of summarized our discussion for the analysis of the laser cavity. Right? Is there any question? Well, I've been trying to slow down my lecture, so we need to move into the next topic. That is polarization, but in fact, we talked about polarization before. Now we just need to develop a more powerful tool for the calculation. So we'll move into the third chapter, or what I call it chapter 2. And in this chapter, you're going to see why engineers and physicists hate each other, because one adopt I, the other adopt J, and so we're going to touch this a little bit, okay? And I and J, in fact, are both the imaginary unit. Okay, I want to give you a little bit incentive to study this. And I've done this to a few students before. And if you manipulate the polarization of light, you can add information into the experiments. And when we do applications, basically we are adding or taking out information, and that is the application, right? And so if we can manipulate the polarization of light, you can synthesize colors. You can synthesize the color from the projector. So if I put a polarizer, you see green color. If I rotate it, you see the color change. So this means that something is doing some trick in the projector. It's quickly change the polarization, or there's some mechanism controlling the polarization so that you see different colors on this screen. Okay, if I do it, if I don't do it, it's white light. If I do it, it's green light. If I rotate it, you see the color change.
Wow.
So this means that you see that the different colors coming out from this, in fact, is polarization controlled.
Actually crazy.
And you can play with this after the class. And so this is sort of incentive for you to understand why we talk about polarization. And in fact, perhaps I can also do this. If I have a laser, well, natural light coming down is randomly polarized. But if I build a laser like this, because the design of the laser, we in fact polarize this laser light. So if I put a polarizer in front of it and try to rotate it, you can just see the attenuation or change of the intensity. Ooh, this is not so obvious, because that is because our human eyes are very sensitive to green light. So you see that this is the quite strong green light, but when I rotate the polarizer, you can dim it a little bit. This is the so this is the after some strong attenuation because of this polarizer. Okay, if I continue to rotate it, then you open up the intensity again. Okay, so this laser light is the more or less polarized. And in fact, when we do nonlinear wavelength conversion, this green light comes from some nonlinear wavelength conversion process. We convert an invisible infrared light into green light. So when you see this green laser, in fact, this laser is the infrared laser. And there's some element inside to convert the invisible laser into green light. And then you can see it. But during the conversion process, we need to manipulate the polarization of the laser to get the green light. And that is why the output of the green light is polarized along some direction. Okay. And so this is the class I'm also teaching in this semester. That is nonlinear optics. All right. So you have some motivation to look into this now, right? Because it's interesting. You see it. You saw it. Stabura, are you interested in this?
Yeah, why not?
Well, thank you for not disappointing me. So anyway, you saw some interesting thing. You change the polarization or manipulate the polarization. You see some display properly sending information to you. All right. We have gone through this briefly in chapter 0. So let's sort of review a little bit, and then we want to talk about Jones matrix so that you have, again, a powerful tool to model the polarization state of light. Okay. So previously we said that the polarization direction of the EM wave is the along electric field direction. So the simplest is the transverse electromagnetic wave, TEM wave, right? This is TEM wave. And then if you could identify the direction of the electric field, then we said this is the polarization direction of the light. All right, everybody understood this. And then I will start to show you something that you really hate to see it. All right. Previously we used J. Now I try to change it to I. I hope I don't confuse you too much, but we'll come back to change it to GA. But just to let you feel that when people adopt different notation, you need to be able to adapt, okay? And the physicists usually just use I, but engineers usually use GA, and they don't quite go along each other anyway. But let's try to change it to I and see what happens, okay? So now we move this KC in front, and then put omega t in the back, and then say that, hey, I can write into this. Right, nothing wrong with this calculation, everything is correct. I extract this and call this phasor. But now my angular frequency now has minus sign in front of it. So I told you that when I get a solution, and then I want to construct a real value, real signal, I need to multiply this solution with this exponential minus I omega t to get the final result. The rest is just the mathematical tools. Okay? So everybody agree, right? Sure, okay? Okay, this is just a mathematical tool. But if I want to get the result, let's just do the calculation. And of course, I can also E, Z, T, I can write this with some sort of, I can write like this, why not, right? And then I can write as the real part, E and 0, exponential on JKZ, multiplied with exponential J omega T. And then I use GA in this expression, and then I denote this as the basis. Okay. So this is the difference. The difference is that when you want to convert your solution back to this the real signal, then you multiply with this. And then let's see what happens. All right. The good thing about this notation is that when you have a wave propagating along z direction, you notice that you have cross sign here, always cross sign. So that is why physicists really like it. You don't struggle with the engineering notation that you have minus GA right here to tell yourself that the field is propagating along cross z direction. You have cross sign here, you have cross sign here. Why not? Let's just adopt this I notation. All right. Any question about this? All right. So let's adopt it. And previously we talked about the wavefront defined by this k vector and also the directional cosine. Cosine alpha, beta, gamma is the angle between the k vector and the x-axis. And beta is the angle between the k vector with the y-axis. And gamma is the angle between the k vector with the z-axis. So alpha, beta, gamma with the cosine, we call that direction cosines, right? So we have this construction, and in the x, y, z coordinate system, this condition, the wavefront equal to a constant will define the wavefront is a plane. So we call this plane wave. Okay? And then we simplify it. We simplify it to allow the wave to propagate along z direction. Previously, it's propagating along some abstract direction, but why now we redefine the coordinate system so that the wave propagate along z direction in this configuration. In this configuration, the z direction is along this direction. Okay, using the right-hand rule. And then, so the electric field can be on the xy plane. For this case, we purposely set it along x direction. And but in fact, in general, we can have two components on this xy plane, consisting of this x component and y components. So in general, you have this x component, y component. Once we have this, then we can define an angle for the polarization. relative to the x-axis. Okay, so there's the angle associated with it. Okay, so now let's just write down that I have two components on the xy plane, and then there's a certain amplitude associated with each component, and that's also open another possibility that the phase could be different. But for this case, let's assume the phase of these components are the same. So we can calculate the angle of this alpha for this electric field. And it turns out that you see that when you do this tangent alpha calculation, you take the ratio of these two components. Turn out this alpha is nothing to do with time. This alpha angle is always fixed, even though the electric field is oscillating like this. But the angle does not change. We call this linear polarization. And you have seen this before, right? So this is quite easy and present review. We studied this in chapter 0. Let's increase one freedom with some arbitrary phase difference between these two terms. While at this moment, I'm still adopting I notation. I put this KZ in front of the omega t, okay? But adopting I notation up to this point does not change the physics, does not change the discussion we had before, okay, up to this point. Now, let's adding this phi, additional phase to this x and y component. And then previously you knew that from the conic expression, well, you can sort of lump this into a variable called c, and then for this, you see these two terms having a phase difference. Okay, just lump the three terms into this, and then you can construct the conic expression. We talked about this in chapter 0 already. And we identified that with this phase difference between the x and y component, you have a ellipse on the xy plane. Right, so you end up having this trajectory of the tip of the electric field on the xy plane. So this is easy because you have seen this in chapter 0. All right, so and there's a slant angle associated with it, but basically this the tip of the electric field just rotating either this way or this way, depending on the side of this angle. Okay, and this slanting angle determined by the this angle, the phase angle difference, and also the amplitude of the two components. Okay, and then human beings like to control. So this is not pretty enough. And make a circle. Okay, we can make a circle. And so let's try to look into the amplitude and also phase. And you see that the polarization state of the light is determined by the amplitude and also the phase difference alone. So why not just simplify this into this expression? Okay, you have the amplitude in front of it, and then you just drop the c, this angle, and then this is the already give you the complete description of the polarization state, and you can start to adopt also what we call the Jones factor. Okay, just two components. Okay, determine the polarization state of the light, including the amplitude and also the phase difference. Here, when you write down the phase difference in complex notation, you have to keep track of I in your expression. Okay, here I write I don't write J. I just write I right here. Okay. So this is Jones Jones factor, and this expression tells you how the polarization state is. Okay, because you have different amplitude and also have a phase difference. So the tip of the electric field will trace out and ellipse in the XY plane. All right, now let's try to take control for this polarization, for the polarization of the light. Let's set this phi equal to plus minus 90 degree, okay? And so you end up having this phi equal to plus minus 90 degree. Then the slanting angle becomes 0, okay? Now you have an upright ellipse like this. Because when you go back to 2 pages before, you have this expression. When this phi equal to plus minus 90 degree, you get theta angle equal to 0. So you have upright ellipse like this. Okay. So you start to manipulate the polarization of the light. And if you set more conditions on it, but you construct different kinds of polarization state. And now we want to know the sense of the rotation of the tip. Previously in chapter 0, we adopt J, okay? And now we'll adopt I, but we do the same calculation. Well, the phase difference is like this, right? So you write into a complex notation. You have plus minus I, pi over 2, and then this is equal to plus minus J. Up to this point, we don't modify anything except converting this the J into I in the calculation. Okay, but the important thing is that when you write I, this two term is flipped, flipped. Okay, and let's see what happens. Okay, when you flip these two terms, you change the sign of the time. Okay, so when you try to write this angle by taking a tangent of these two components, you end up having this expression. But these two terms flip, and you are adding a minus sign to the time. So when you see somewhere, set this z equal to a constant value. Previously, when you use J, the angle increase with time, now becomes angle decrease with time. Okay, when you adopt the I notation. And quite often that in your textbook, you adopt I. So I need to talk about this part so that you can sort of switch back and forth between engineering the concept and also the physics concept. Okay, previously we have omega t minus kz. So when we talk about the angle change versus time, previously if I have an increase of the angle over time, now I have the decrease of the angle over time if I adopt this I notation. Okay, but that is just a matter of definition. Okay, you just keep track of the I or J in one system only. If you adopt I, then we talk in the language of I. If we adopt J, we talk in the language of I. Okay. Now we talk in the language of I. Okay. Now you have this result. Let's set this z equal to 0 to simplify the discussion, and then assume that we are standing on this plane in this plane. So when you have this, say minus sign, when you have minus sign, this minus sign is going to cancel with this minus sign. So it's going to tell you that this angle is going to increase with time. When the angle increases with time, it's going along this counterclockwise direction. Okay, so this is associated with phi equal to pi over 2, and then you have plus I right here. And we call this left-handed polarization, because going this, right-handed polarization, because going along this direction, I need to use my right hand pointing along z direction, and then this 4 fingers is going this direction. I'm using my right hand. Okay. Now, if I adopt a solution that goes with this plus sign, this is negative. So this means that over time, the angle is going to be reduced to this minus sign. So you're going to get a rotation like this. That is the clockwise rotation. Okay, so I'm adopting this solution that comes from this minus sign. So that goes with this minus side solution. And if I want to follow this direction, I need to use my left hand with my thumb pointing toward the z direction. So we call this left-handed polarization. But in physics textbook, it will tell you that, hey, this is rotating to your right. Let's call this right polarization. Oops. Students run into the confusion. Okay. But that is the reality, because the physicists and engineers talk in slightly different language. Okay. And this goes to your left, then the physicist will say that, hey, this is left polarization. So in the handout, the first part of the handout, we go with I, and then we follow the language developed by physicists. But then quickly, I'm going to bring you back to the engineering notations. Okay. So this is a little bit new to you, because we started with the engineering notation at the beginning of the class. But this is just sort of some flavor for you, so that you can study your textbook and also study some other of this textbook. All right, is there any question? So a short conclusion is that the sign before this I determines the sense of the rotation. Okay, and then those are just the language the people establish for description. Okay, for describing the polarization state of light. Well, circular polarization is that you set additional condition to set these two magnitudes to be the same. The amplitude of this x and y component are the same. Then also you keep the 90 degree plus minus 90 degree phase difference. Then you end up having a circular polarization. Okay, and again, this plus minus sign determines the sense of rotation. Okay, so this is the same as before, except that the tip of the electric field will just trace out a circle. Okay, and again, there's a right-handed circular polarization, left-handed circular polarization, and this is the sort of language adopted by engineers. If you want to adopt the language by physicists, then this is the left circular polarization, and this is right circular polarization. Okay, if you see this H, this means that you need to use a hand to be consistent with this language. Okay, if there's a H in this description. So I hope that this is not too difficult, because it's already tell you that the H means that you need to put your hand in front of this to decide this right or left. All right, so this is sort of the I notation for describing the polarization state of light. All right, I want to stop here and continue on Wednesday online. And then next Wednesday, don't forget that we're going to have a meeting exam number 1. I will see you online on this Wednesday. Okay. And if you want to play with the polarizer, you are welcome.